In part 3 of our lesson on angles, you will learn about angles in standard position and coterminal angles. When an angle is in standard position, that means that the initial side of the angle is on the positive x-axis. So in the xy plane, we know there's the positive x-axis, the negative x-axis, the positive y-axis, and the negative y-axis. So that means that all angles in standard position will have their initial side beginning here on the positive x-axis. Now in your algebra class, you often use x's and y's as your variable. It's really common in trigonometry to use theta as the variable to represent angles. Now looking at this first example, we want to label one revolution where theta is positive. So remember, in standard position, that means this positive x-axis will be the initial side of the angle. So that will be 0 degrees. So if the terminal side of the angle and the initial side of the angle are both in the same place, that means the angle will be 0 degrees. Now if we let the angle open up all the way here to the positive y-axis, that would be 90 degrees. Then that means that any angle whose terminal side falls in between the positive x-axis and the positive y-axis is going to have an angle measure between 0 and 90 degrees. Now starting from the positive x-axis, if the angle terminal side goes all the way to the negative x-axis, then that would be an angle measure of 180 degrees. So an angle whose terminal side lands in quadrant 2 here would have to have a measure between 90 degrees and 180 degrees. If the terminal side of the angle goes all the way to the negative y-axis, we know that would be an angle of 270 degrees. And so if the terminal side's in quadrant 3, that means theta would be between 180 degrees and 270. And if the angle opened all the way around back to the positive x-axis, we know that would be 360 degrees, which would mean if the terminal side is here in quadrant 4, the angle measure is going to be between 270 and 360. Now in trigonometry, angles can also be negative, so we're going to now label one revolution where theta is negative. All angles still begin at the positive x-axis, but going in the negative direction now, we would have negative 90 degrees. Going around here, this would be negative 180 degrees. Coming to the positive y-axis would be negative 270 degrees. Then coming full circle will be negative 360 degrees. Now, angles whose terminal side lands in quadrant 4, you can see will have to be between negative 90 and 0 degrees. Now I have to put the negative 90 degrees first so that the inequality will remain true, because negative 90 is less than 0, not the other way around. Then if the terminal side is in quadrant 3, we know those angles will be between negative 180 degrees and negative 90 degrees. If the terminal side lands over here in quadrant 2, then that will be between negative 270 and negative 180 degrees. And if the terminal side is in quadrant 1, then those angle measures will be between negative 360 degrees and negative 270 degrees. Now, a quadrantal angle is any angle whose terminal side lands on an axis. Let's first label the quadrantal angles. So we know that 0 degrees lands on an axis, 90 degrees, 180 degrees, 270 degrees, 360. Now, it doesn't stop at 360. An angle could begin here on the positive x-axis, rotate all the way around, and keep going. So from 360, we would have to add another 90 degrees, and we would be at 450 degrees. Then if we kept going from 450 degrees, then this angle going all the way around to there would be 540 degrees, and so on. Now, if we go in the negative direction, we know starting from 0, if we go this way, we know this would be negative 90. We know over here would be negative 180, negative 270. We get negative 360 here. If we kept going, we would get negative 450, and so on and so on. Now, naming all of the quadrantal angles one by one would be impossible, since you can see there's going to be infinitely many of them. So we'll use set notation to list all the quadrantal angles. So I'll start kind of in the 0 position here. It might be easier for you to see. From 0 degrees, we would go 90, 180 degrees, 270, and then we can say etc. And then going in the negative direction, we would have negative 90, negative 180, and then etc. So this infinite set here lists all the quadrantal angles. Our next topic is coterminal angles. Now, coterminal angles are angles that share the same initial and terminal sides but have different numbers of rotations or different directions. So they start with the same side, they stop with the same side, but their rotations or directions can be different. Now, each of the next examples has two parts. In the first part, we will draw the angle in standard position, and secondly, we'll find the smallest positive coterminal angle. So in this example, theta is equal to 435 degrees. Now right away you see that that's bigger than 360, so we know we're going around more than once. If we label the next quadrantal angle after 360, add 90 degrees, we get 450 degrees. So we know that 435 is going to be in between 360 and 450. So here's 435. And now to show the rotation, you start on the positive x-axis where the initial side is. You show that you rotated all the way through and stopped at 435 degrees. All right, now we're ready to find the smallest positive coterminal angle, and that angle has to have the same initial side and the same terminal side, but we want it to be the smallest possible positive angle, so that would be this angle. And the way we can find its measure is subtracting 435 and 360. To get 75 degrees. So the smallest positive coterminal angle ended up being 75 degrees. And it's important for you to understand that 75 degrees is different than 435 degrees. 75 degrees means you only rotated that much, where 435 degrees means you rotated all the way around and then 75 degrees more to get to 435. In the next example, theta is equal to 1,270, so that's definitely more than one rotation. We know we would have 0. If we went all the way around, that would be 360. Going all the way around again, so we would add 360, that would be 720. Add another 360, that would be 1,080, so we're starting to get closer. So maybe we'll go ahead and add 90 to get the next quadrantal angle, so 1,170. Let's add another 90, 1,260, and we can see that 1,270 is just going to be 10 more beyond that. So that would be here. Now when we draw in the angle, we have to show the rotations. So we start at the positive x-axis, and this would be 360, 720, 1080, and then we stop at 1270. So that's drawing the angle in standard position. You have to show that rotation. Now in part 2, we have to find the smallest positive coterminal angle. So that would start with the same initial side in standard position, and it would end at the same terminal side, but it would be the smallest possible rotation to get there in the positive direction. Probably the easiest way to think of finding this measure is to start here, go to the negative x-axis, we know that would be 180 degrees, and then from 1260 to 1270, we know that that's just 10 degrees more. So that would mean that smallest positive coterminal angle is going to work out to be 190 degrees. Now another way you could have determined it is to take the ending angle, 1,270, and from there back up to the previous angle that would be coterminal at the initial point, which is 1080. So subtract 1080, and if we do that subtraction, we also get 190 degrees. In this next example, we have our first negative angle to consider. So we start with 0, but this time we go in a clockwise direction. So we would have negative 90 is here, negative 180 is here, negative 270 is here. So we know that negative 250 will be in between those two. And here is the rotation that we would have. Now in part 2, we have to find the smallest positive coterminal angle. It's CYU time, so pause the video, work the example on your own, then restart the video to check your answer. Okay, let's see how you did. Remember, we start at the positive x-axis and draw the shortest rotation to get there. A couple ways to figure out this angle. Starting here at the positive x-axis and going to the positive y-axis, that's 90 degrees. We can see that the angular displacement between negative 270 and negative 250 is 20 degrees. So 90 degrees plus that 20 degrees tells us that's 110 degrees. Another way that you can think of it is, since we're going in the negative direction, this was negative 250. If we had gone all the way around, we would have gone to negative 360. And you could say negative 250 minus negative 360 becomes negative 250 plus 360, which is equal to 110 degrees. So that smallest positive coterminal angle is 110 degrees. In this next example, theta is negative 410 degrees. It's CYU time, so pause the video, work the example on your own, then restart the video to check your answer. Okay, let's see how you did. So we'll start by labeling the quadrantal angles. We know it's going to be more than one rotation. If we kept going in the negative direction from negative 360, we know that this would be negative 450, which means that negative 410 is going to be between them. And we indicate the rotations all the way around plus a little bit more to get to the negative 410. So now we're ready to find our smallest positive coterminal angle. And remember, it is positive, so it has to go in a counterclockwise direction. And probably the easiest way, again, would be to just notice that between negative 360 and negative 410, that angular displacement is 50 degrees. So if we start at 0 and go to the angle, we know it would be 50 more to get to 360 degrees. So we could do 360 degrees minus that 50 degrees to discover that we have 310 degrees. So that's our smallest positive coterminal angle. Now in this example, we're being asked to find a formula for all possible angles, theta, that are coterminal with 20 degrees. So first, let's draw in our 20-degree angle. That would be about here. It would have this rotation, 20 degrees. Now, to get back to this angle again, remember coterminal angles are going to start here on the positive x-axis, and they have to have the same terminal side as the 20-degree angle, but they can have different rotations or directions. So we could start here, go all the way around, pass up the 360 degrees, and end up there again. So in other words, if I'm at the 20 degrees, I have to add 360 degrees more to get back there, or I could go around 2 more times, so I could have added 2 times 360 degrees, or I could go around 1, 2, 3 times more and end up there, on and on and on. Or we could go in the reverse direction. If we were on the terminal side of 20, we could back up by 360 degrees. So we would subtract 360 degrees. Or we could do 2 times that, so it would be negative 2 times 360. Or it could be 3 times in the negative direction, so it would be negative 3 times 360. So I think you get the idea now. Notice that all of these are just integer multiples of 360 degrees. There are going to be infinitely many angles that are coterminal with 20 degrees. So we know we can't list them all since there are infinitely many, so we have to come up with a formula. We're going to let n equal an integer, and that's what all these coefficients are. So remember, the integers, dot, 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 negative 2, negative 1, 0, 1, 2, dot, 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 then our infinitely many number of possible angles, theta, is going to equal that 20 degrees where we started off, plus any number of full rotations. So plus n times 360 degrees. And so this formula will generate all the possible angles that would be coterminal with 20 degrees. Next, we have a CD player that spins a CD at a rate of 480 revolutions per minute. And so that's what's pictured here. This disc is revolving at a rate of 480 revolutions per minute. And the first part of this question asks, through how many degrees will a point on the edge of the CD rotate in 1/2 of a second? So this 480 revolutions per minute, that is a rate. So the rate that the CD spins is 480 revolutions in 1 minute. That's what RPMs mean. Now we notice that the question asks us through how many degrees. So we don't want units of revolution, we're going to want the units to be degrees. So let's use a conversion factor that 1 revolution is equal to 360 degrees. We also notice that the question has units of time in seconds, not minutes, so we can go ahead and convert the minutes to seconds by multiplying by a second conversion factor, that 1 minute is the same as 60 seconds. Now, when we multiply all this out, we multiply 480 times 360 and then divide by 60, or of course we could cancel 60 into 360 6 times and then multiply that times 480. We get 2,880 degrees per second would be the units. Now here's how the units worked out, right? We had revolutions here, which canceled with revolutions here, and we had minutes here that canceled with minutes here, so you can see that we were left with degrees over seconds, and that's what we had for our rate. Now the question is asking us to find how many degrees, not how many degrees per second. So that's where the unit of time will come in. So now the number of degrees is going to equal the rate times the time. So we have 2,880 degrees per second that we're going to multiply by 1/2 second. Now, pretty easy multiplication to do. Half of 2,880 is going to be 1,440. And now let's take a look at the units. The seconds in the denominator here are going to cancel with the seconds, which are in the numerator there, right? This is seconds over 1. And so the only units that are left are the degree units. So the point on the edge of the CD that's revolving at 480 revolutions per minute, that point will rotate through an angle of 1,440 degrees in 1/2 second. Now there's a second part to this question, which asks us through how many revolutions did the point rotate in that time. So we have 1,440 degrees, and we want to convert that to revolutions, so we use a conversion factor that says 360 degrees is 1 revolution. Now the reason I knew to put degrees in the denominator is because that's what I'm trying to cancel out, and I want to be left with units of revolutions. So now we do that division, 1,440 divided by 360, and that works out to be 4 revolutions. And we can double check our units because the degrees here are going to cancel with the degrees here, and we're left only with the revolutions.